With the establishment of Henrietta Leavitt's law and Hubble applying it to show that there are other galaxies, it became clear that they definitely exist. And as years went on, we started discovering more and more galaxies. However, it is important to try to ask the question, what is a galaxy anyway? You could think that a galaxy is simply a set of stars, and perhaps have a definition saying a galaxy will be a galaxy if it has more than X number of stars. Behind me, you can actually see real data of different objects. It turns out that only some of these objects are galaxies, while others are actually stellar clusters. Now, to understand the difference, we really need to look into the details of, for example, the orbits of stellar clusters versus the orbits of stars and galaxies. During the 60s and 70s, everyone thought that galaxies would rotate pretty much like our own solar system. If you had stars that are closer to the galactic center, they would be moving faster. If stars were further away, then they would actually be moving slower. In a way, with very simple considerations, essentially equating gravity with a centripetal force, you could actually make a very simple prediction. Given that we could measure the mass of a galaxy, we could know essentially how the velocity would vary once you go beyond the radius that contains all the mass of the galaxy. Up to that point, because you're going from the galactic center to the point where you then be encapsulating all the matter, the rotational velocity is actually expected to go up. But beyond that, because there's no extra mass, we would expect the rotation curves of galaxies to just be Keplerian, essentially look like the solar system. And this is because of this dependence of square root of 1 over r. It turns out that this is not the case for galaxies at all. The first observations to show that galaxies do not rotate like solar systems even beyond all the visible mass came from Vera Rubin that you can see here. What she did was essentially observe some spiral galaxies and actually take spectra of these galaxies as a function of distance. Now, by using the Doppler effect, she could actually convert shifts of wavelength, positive and negative, in terms of velocities. And if galaxies were rotating like solar systems, you'd actually expect these things to go up and then they should go down. But instead, they just keep at the same level all the way to really large distances. And the important thing to realize is that essentially all stellar light stops here. She could do these observations because beyond the radius that essentially contains all the mass, there's still some very diffuse gas. It contains very little mass, but it can be used to actually do these observations. And by using the Doppler effect, she was able to actually convert this into a velocity. This allowed her to actually derive this incredibly important result, first for Andromeda, and then for many other galaxies. Now, it turns out that instead of rotation curves going down, in reality, they actually stay dramatically constant at a velocity of very close to about 200 kilometers per second. Now, the reason why this discovery was so important is that if you look at this equation, the only way you can actually get the velocity to stay constant as radius increases is if mass is actually increasing at the same rate as r. In other words, the only way we could think of, especially at the time, and the modern way of interpreting these observations, is that m is essentially a linear function of r. And in other words, even beyond the radius that we thought contained all the mass, there's actually more and more and more mass that we cannot see. Something like 80% of the mass in many galaxies is in this form, and this is what we call dark matter. It also turned out that Andromeda was not the only galaxy to show these rotation curves, and once Vera Rubin started measuring it for many other spiral nebulae and other galaxies, we realized that essentially every single galaxy showed the same rotation curves. They would go up to the point that we could see all the observable mass, and from that point onwards, for larger radii, then anything that was there, essentially diffuse gas, is moving at essentially a flat or constant speed, which can only be explained if you have an extra mass that we cannot see, but is actually dominating all the dynamics at those radii. Soon after, we realized that also our Milky Way is no exception, and the Milky Way also shows a relatively flat rotation curve. We would expect it to go down like here if it was Keplerian, but it actually does not. And also we know that the sun is orbiting around the galactic center at something like 220 kilometers per second. What these observations of our own galaxy allow us to understand is that essentially, because of the distance that the sun is from the center and its age, we know that the sun actually went around the center of the galaxy approximately 20 times. And also that we go around the galaxy once every 250 million years. The galaxy itself, we expect that the oldest stars actually went around it something like 61 times. So we could say that our galaxy is about 61 years old. And for context, life on Earth appeared about 15 galactic years ago. It means life has existed on Earth while Earth went around 15 full rotations of our galaxy. Now, coming back to this very important question of what a galaxy is, perhaps we should define it. In modern terms, a galaxy is not simply a set of stars, but instead, you can think of a galaxy as really a massive gravitationally bound system that contains stars, but also interstellar medium. And this interstellar medium contains both gas and dust, but also an important component of a galaxy is dark matter that typically dominates it. And the presence of dark matter is really what sets apart this set of stars, interstellar medium, gas, and dust, and this system of stars, interstellar medium, gas, and dust. This one contains dark matter. This is an actual galaxy. This is a globular cluster, and it is not a galaxy. You'll be able to find all these details in the lecture notes and also as a question that has full solutions. But perhaps one of the things that should be pointed out is that by conducting observations which are very deep, such as the Hubble Ultra Deep Field that you can see on my background, we realize that essentially every point in the sky contains something like 10,000 galaxies. Because we know the area that the Hubble Ultra Deep Field covers, and we know the full area on the sky, that's 4 pi in steradians, or 41,250, more or less, square degrees, we can actually extrapolate this number of galaxies to the full sky. On top of that, we actually know that the Hubble Ultra Deep Field, even though it is the deepest image ever obtained, it actually misses a lot of galaxies. And we know that there's at least 70 to 80 times more galaxies than we can see in this picture. Therefore, by combining all this information, we can actually estimate, and this is one of the best current estimates, that there are at least 2 trillion galaxies in the full observable universe. That's 2 times 10 to the 12 galaxies. And in addition, because we can now measure the full observable universe, we can also update our cosmic insignificance. And I would encourage you to also try to reproduce these numbers that are shown in the lecture notes.